So welcome to the CIMAT Colloquium. It is a pleasure to have Dr. Ivan Nourdim. Ivan Nourdim is a professor at the University of Luxembourg, working on probability and in particular in stochastic processes and their convergence. Ivan is really extremely productive, but he's very young and he has already more than 100 papers in really top journals in probability, such as probability theorem related fields, analysis of probability, analysis of in situ and Ray Poincaré. And for this, he has been winner of various prizes, including the prize of the Fondation de Sciences Mathématiques in 2011, the prize of Francis Scopus Researcher Award in the field of mathematics in 2013, and the prize of FNR for studying publication. And he has already 2 books on his topics of interest. One is in normal approximations with Malevin calculus, from statistics method to universality, and the other one is called Selective Aspects of Fractional Brownian Motion. Today he will talk about the functional BREUER-MAJOR theorem. So thank you very much, Ivan.
Yeah, thank you very much for the nice introduction. So if you don't mind, I will stop my video just to save some load. Okay, and so I will use my tablet to make the talk, like a whiteboard. So it's a pleasure to give this talk in front of you today. I'm going to speak about the functional BREUER-MAJOR theorem. So don't worry, I will explain everything, all what it means. So just for me not to forget, let me say that this is based on a joint work with David Nualart, published this year. Okay, so I will start with a very simple setting. So let me consider X, which is a square integrable random variable. And so let me assume to have a simple setting that it is centered. And let me write the variance of its sigma square, so which is this finite. Okay, now I consider copies of X, so X1, X2, etc., independent copies of X. Okay, and so just need to fix the notation. So if I remember the CLT, so we know that we have 1 over square root of n, x1 plus etc. xn converge in distribution to the Gaussian random variable with variance sigma square. So this is just the usual CLT. Now let me do this observation. Very easy observation that my x, my random variable x, can be always represented, so in law, as a function of a standard Gaussian. So where G is a standard Gaussian. And so there is nothing deep behind this. This is exactly the same statement than when you say that any random variable, discrete or continuous, can be always simulated using the uniform distribution. So you know this is an exercise for our students. So here's a phi. You can take for the phi the pseudo inverse of the cumulative distributive functions, and then you apply it to the distribution function of the Gaussian distribution. Okay, so you can it's immediate to check that if I choose for this function, if I choose this function phi, then my x has the same law than phi of G. And so why I am doing this observation? Because now I can rephrase the CLT by saying the following. So let me know, instead of fixing an x, let me fix a phi, which is a square integrable, but this time with respect to the standard Gaussian measure. So let me call it gamma. So gamma is just a standard Gaussian measure. And so let me, for simplicity, also assume that it is centered. So meaning just in this context that the integral of phi against gamma is 0. Okay, now let me, instead of this x i's like in the CLT, let me consider now G1, G2, etc. be independent standard Gaussian. And so let me also set sigma square is a variance of phi of G1, which is well defined because phi is square integrable with respect to the standard Gaussian. And now the CLT, so exactly the same statement, tells you that 1 over square root of n, phi of G1 plus etc. phi of Gn converge in distribution to the Gaussian with variance sigma square, right? Okay, so this is a way to say the CLT, which is a bit different than usual, and which is closer to what I would like to explain with the BREUER-MAJOR theorem. Okay, now I would like to understand how we can drop the independence assumption. And so if we want to remove this independence assumption to understand what happens if the GIs are no longer independent, can we still have convergence in law to the Gaussian? So to a certain extent, we can hope this because of the continuity of the dependence somehow. So now let me consider this context. So I still have my function phi, so which is still square integrable with respect to the Gaussian measure. And let me assume, to just simplify and to avoid subtracting the mean, that it is center. And now let me this time assume that the GIs are still standard Gaussian, but no longer independent, but stationary. So be a stationary Gaussian sequence. So which is a way to extend or to have something more general than independence. And so let me call R the covariance. So with covariance R. Okay, so it just means in this context that the covariance of GKGL is just RK minus L. This is what I mean by covariance R. Okay, so here my new assumption is that this is stationary. Just some remarks. So maybe I keep this for the next sheet. Okay, up. Okay, just a remark. Of course, R of 0 is 1. And the previous setting, so independence, the case where they were independent, is just equivalent to say that my R is given by 1 if k is 0 and 0 otherwise. So this is just to be able then to compare with the usual CLT. Okay, and now I am in a position to state the BREUER-MAJOR theorem, which will tell us under which condition we still have convergence of partial sums of phi of GIs. So this is a result from the 80s, so 83, and the statement is as follows. So let D, which is bigger than 1 because I assumed phi to be centered. So let me say what is D. So be the Hermite rank of phi. So what is the Hermite rank? It is just, so let me say this way, because phi is square integrable with respect to the Gaussian, the standard Gaussian density, it is, you can expand it in terms of Hermite polynomials. And the first non-zero coefficient in this expansion is called the Hermite rank of phi. So I know that my phi can be written like sum of AQ, HQ, where the HQ are Hermite polynomials, and the AQ are coefficients. And here I assume that AD is non-zero. So this is the first non-zero coefficient of phi in the expansion in terms of Hermite polynomials. And I know that this D is bigger than 1 here because this is equivalent to say that phi is centered. Right? Because I assume phi is centered, D is necessarily bigger than. Okay, so I have this D which is attached to phi. And now I will make an assumption. I will assume that R, the covariance function of my stationary Gaussian sequence, is D integrable. So let me assume that this sum here is finite when you sum over Z or over N by symmetry is finite. So this condition is an interplay between a property on phi, so the Hermite rank, and of the Gaussian sequence, the R. And under this assumption, what is very nice is that this is enough to ensure that my quantity of interest still converges to the Gaussian law with the same usual rate, 1 over square root of n, where sigma square here this time it is not that as easy as in the case of independence, but this time it is given in terms of the Hermite coefficients of phi. So more precisely, we have this explicit or pseudo-explicit formula because it is given as an infinite series. So we have the sum over q of factorial q aq square, and then the sum over k of rk power q. And so this is part of the conclusion that this guy is positive, which is not very difficult to prove, and also finite. Okay, and this is exactly the BREUER-MAJOR theorem. So it gives a sufficient condition under which we still have the same conclusion like in the CLT. And of course, it contains the CLT as a particular case, because in the CLT, whatever D is, this condition is always satisfied because R is 0 everywhere except at 0. Okay, so let me give you a bit of history behind this result. So before I explain what I did with David. So in the 80s, so we had the original, these original papers, the original statement and proof, and the proof of this result was by the diagram formula. So what was the proof of this result? So how Breuer and Major did prove this theorem? They just computed all the moments of this quantity here. And the way to do this was to expand phi in Hermite polynomials, and then by computing the moments to represent this using the so-called diagram formula. And then they had to see, to understand why in the limit you get exactly the moments of the standard Gaussian. Actually, they did not use the moments, but the cumulants, which is completely equivalent. And so at that time, people who did a lot around this thing was some names just was Taku. So Taku was more interested in the non-central limit theorem. So in the case where this condition here is not satisfied, so in the case where you have equals infinity here, and in this case, he was able to prove that still the partial sums, but divided not no longer with square root of n, but with n to some fractional powers, depending on some assumption on R, converges in law not to the Gaussian distribution, but to the so-called Hermite random variable. So I'm not going to speak about this today, but we know also what happens in the case where this sum is infinite. And also we had extensions, multivariate extensions and so on by Archons. And also I would like to mention these two guys, Chambers and Slud, because I will, I will go back to these two guys in some minutes. Okay, and so Taku and others, also the Brownian, prove that, showing that the BREUER-MAJOR theorem, this condition is sufficient, but somehow also necessary, because in the case where you have that this sum is infinite, then the normalization is no longer square root of n. So is no longer square root of n. And the limit you get is not the Gaussian, it is so the Hermite random variables, and they belong to the Diez Wiener curve. Okay, so yeah, it's another story. But also it was very interesting at that time that we found the phase transition phenomenon. So this quantity, the sum of Rk power d in absolute value, was exactly the condition under which you get either the Gaussian, like in the usual CLT, or something else. Okay, so many other developments was done after. And here, just I wanted to mention, so maybe 10 years ago, something like 10 years ago, together with Giovanni Peccati and Mark Podolsky, we gave another proof of the BREUER-MAJOR theorem, and we were also able to calculate rates of convergence with the total variation distance and some other things. And we used the so-called Mayer-Stein approach. And why do I mention this? Because it was a step that, a new proof that was completely analytical somehow. So no longer combinatorics. And so this change of point of view allowed to go further because it was quite difficult in the 80s and to apply the diagram formula in situations which are not so as nice as in the BREUER-MAJOR theorem. Here with the Mayer-Stein approach, you have a completely analytical proof, and then you can expect to go beyond the case, stationary case, for instance, or other extensions. So today, what is the purpose of my lecture today? I'm interested, like I said in my title, what about the functional version? So, of course, this is a natural question for a probabilist. If you manage to prove a limit theorem, central limit theorem here, you would like also to understand what happens if you make the time appear. Can we obtain convergence to Brownian motion, for instance, instead of just simply the Gaussian? And actually, if you read the original paper of Breuer and Major, you will see that they already thought about this, and they get the FDD convergence already. So let me just rewrite the situation. So we have a phi which is square integrable with Hermite rank D, so bigger than 1, which is equivalent to say that phi is centered. So we assume that this sum is finite, so R is D integrable. And without further assumptions, so just under the same condition that we already mentioned in dimension 1, we get that the quantity of interest, but this time we stop not at n, but at the entire part of nt. And then we just put phi of gk. So this quantity, it is shown by Breuer and Major. So it's some sort of multivariate extension of their one-dimensional result, converge, as we can guess, to sigma wt, where w here just refers to a standard Brownian motion. Okay, so if you take different times, so for instance, you can restrict to the compact interval 0, 1. So if you take times in 0, 1, as many as you want, you get this FDD converge. Okay, but then, of course, and certainly they were also interested in this problem, but there is some difficulties here. They wanted certainly also to understand what happens if you look at this convergence in the space of càdlàg functions with a Skorohod equipped with a Skorohod topology. So let me consider D, so the space of càdlàg functions equipped with a Skorohod topology. And can we extend this FDD convergence to a convergence, a functional convergence in D? Okay, so first reflex, if you want to do so, is to look at the classical reference on the subject, the Billingsley book. And so if you look at Billingsley book, one of the last version, you will find this theorem 15.6, and you will refresh your mind and see that tightness in D, which is what is missing to prove that when you have FDD convergence, the only thing you must check to get functional convergence is that tightness is satisfied. So tightness in D holds for a sequence, let's say a sequence of processes in D, let's call them Yn. So it holds for Yn if there exists some epsilon, positive epsilon, there exists some eta positive, there exists a constant C, and then the criterion is that you must bound the expectation of Ynt minus Yns, so power eta, by this constant C. And then what is important in D is that you must prove the entire part of Nt minus entire part of Ns divided by N, power 1 plus epsilon, and this must hold for any S and T between 0 and 1. Okay, so this is the usual criterion. So here, let me just stress that, okay, so we have this eta here. And here, somehow this eta is related to this 1 plus epsilon, in the sense that if you look at what Breuer and Major proved already, so we get convergence to the standard Brownian motion. So we can expect somehow that the eta is related to 1 plus epsilon, in the sense that if you expect the limit to be the Brownian motion, then you expect that 1 plus epsilon is given by eta over 2. Right? And so an equivalent way just to remove these two parameters, we are going to check this, that tightness holds in the holds for Yn. And now let me take a Yn for which I know already that it converges FDD to the standard Brownian motion. So in this case, I can assume that, or I can try to check that there exists a P strictly greater than 2 and a C. So now I only have 2 parameters instead of 3 in the previous statement. And let me write using norms because it's going to be easier to use later. So I look at the LP omega norm of the difference Ynt minus Yns, and I must then check that it is less than Nt minus Ns divided by N, and no power 1/2. Okay, so here it is not equivalent to the previous statement, but here it is what you should prove to hold when you know already that your process converges to the Brownian motion. And here, let me just point out that my P here must be strictly bigger than 2. Which is a pity. I will explain why. Because why strictly bigger than 2? This is because otherwise you won't get something here which would be strictly bigger than 1. Okay, so if you want to have something here strictly bigger than 1, you need this P. When you just rewrite what this criterion means here, you will see that the P must be strictly bigger than 2. And so imagine just for a moment that this P would be allowed to be 2, P equals 2. So in this case, it would be very easy to check because here you would get the L2 norm. And because Hermite polynomials, when you apply this to this sequence, because Hermite polynomials are the orthogonal polynomials associated to the Gaussian measure, it would be very easy, it is very easy to calculate the L2 norm or to evaluate the L2 norm of the difference of Ynt minus Yns. But if you want more than the L2 norm, like here the LP norm with P strictly bigger than 2, then you have to deal with this problem, and it is not that easy. For instance, you can try with p equals 4, and then you will get very difficult quantities and so on. Okay, so the rest of the talk will be focused on trying to prove that such an inequality holds when for yn I consider this quantity here. So yn will be 1 over square root of n sum of phi of gk. Okay, of course, we are not the first to look at this functional version. So let me mention previous work on this. So we are not the first to look at this functional version of Breuer-Major. And I suspect that even Breuer and Major tried to do themselves in the 80s, but the tools were not available at that time. Yeah, I'm going just to mention two papers which are quite important. So Chambers and Slut, so the two guys I mentioned in my history. This is a paper in PTRF 89. And then a slight improvement, because you will see that this is an improvement, but you don't gain too much, by Ben Harris, who was a PhD student of Jean Bretagnol, in 2002, published in the Journal of Multivariate Analysis. And so let me just give you Ben Harris' condition, which is very close to what Chambers and Slut did also. So Ben Harris' condition. Yeah, so let me write like this. So reads as follows. So what Ben Harris found is that if phi, so you remember that my phi is sum of AQ HQ, Q from D is the Hermite rank of phi to infinity. So here you remember that D is bigger than 1 and AD is non-zero. So if we have such a phi, just to fix the notation, then tightness holds. So I just write tightness hold to mean that tightness for yn given by 1 over square root of n sum of phi of gk. So holds as soon as, and now let me write Ben Harris' condition, there exists r strictly bigger than 1, such that sum over q between d and infinity, square root of factorial q, absolute value of aq, and then sum of rk power q power 1/2, and my r power q is finite. Okay, so this is what Ben Harris found to ensure that tightness. So before I describe what we obtained with David, let me make some comments. First, so I say that Ben Harris is a slight improvement of Chambers and Slut. So let me just mention what Chambers and Slut condition was. It was the same statement, but not there exists R strictly bigger than 1, but they chose to work with R is 3/2, which was quite arbitrary to get something simple, I think. And they did not have in the sum of rk power q 1/2. So without this in the expression. So that is the condition was that if the sum of square root of factorial q, aq, and then 3/2 power q is finite, then we have tightness. Okay, somehow to add this helps a little, just a little, because this is something that goes to 0, but not very quickly in examples. So it is not it is nice to have it, but if you don't have it, the examples you get using Ben-Harris condition with respect to the one you get using Chambers and Slood are not very different. Okay, and why this is not a problem not to have this sum of Rk power q, because just the sum of Rk power q, you can always bound it by the sum of Rk power d, where d is the Hermite rank, which is something that does not depend on q, so you can just remove it from the condition. And this is because Rk is less than 1, because you remember that this is the covariance of gr, let's say gr plus k, and they are both standard Gaussian, so just by Cauchy-Schwarz, this is bounded by 1. Okay, so but now let me focus on Ben-Harris condition. You see that it's not that easy in general to check that this quantity is finite, the quantity I framed in Brown, because you have these absolute values. That is not very natural in general when you are dealing with coefficients. If you put absolute values, it means that you cannot use the sign of AQ to get the convergence. And also we have this R here to the power Q, and in order to check this condition, at least we have to know or to have some information of the coefficients of phi. But sometimes I give you a phi and it's not that easy to compute the Hermite expansion, so it's not even easy to check that such a condition is satisfied. So sometimes such condition can be satisfied, but you don't know that this is satisfied because you don't have access to an explicit expression for the AQ. Okay, so the proof by Chambers and Slood and then the improvement by Ben-Harris was quite tricky and quite difficult. So it was a nice proof, but then we realized with David that there is a very short proof. So maybe I can give you the proof, and you will understand where this comes from. So of course, this is not the original proof, but we are going to explain exactly how this frame condition comes from. So remember that my yn of t is the sum of k from 1 to the entire part of nt of phi of gk, and my phi, just to remember use the notation, is sum of aq hq q from d to infinity. Okay, so maybe just to keep this on the same sheet, I take this, I copy, and I open a new page. Okay, and then we will go back because when I will show you the condition we get by this short proof. So you remember this was my Billingsley statement here, that if I want to check the tightness in D, I have to consider this quantity here and to bound it by something like this. Okay, so let me do this. So I start with y and t minus y and s LP omega norm, and for the moment in my mind p is strictly bigger than 2. Okay, so first of course I can plug the expression of y and t and also replace phi by the sum of aq hq, and so if I do so and I start with the sum over q, I get that this is the sum over q, aq, and then I have 1 over square root of n. Then the increment, so it means that my sum over k is between ns plus 1 and nt here. And then I have Hermite polynomials evaluated in gk. And finally, LP omega norm. Okay, and now first we are going to understand why do we have these absolute values here. This is just triangle inequality for the LP norm. Okay, so I'm just here bounding. So this is a triangle inequality, so nothing very deep. So I just say that this is less than the sum over Q. So then I have AQ. And then I put my LP norm here. So sum of AQ GQ between NS plus 1 and NT LP omega. Okay, and now I observe something which is here. Our simple proof comes from here. We observe that this guy here belongs to the Q's Wiener curves. So it is quite specific. So if you don't know what it is, so most of you know, but if there is at least one that does not know what it is, I'm not going to explain, but what you should just know about this is that this is a particular set of random variables having a specific form. And when each time you have a random variable, let me call it U in HQ, you can bound the LP norm by hypercontractivity. So this is a hypercontractivity property. You know that all LP norms are comparable. Meaning that are equivalent, meaning that the LP norm, even if P is strictly bigger than 2, we know that this is less than P minus 1 over Q power Q over 2, and then the L2 norm. So here the interest is that somehow I bound my LP norm by an L2 norm, and I have even an explicit constant. So let me do this here. So what do I get if I do this? I get that I have also still this term. Then I have AQ. And now I'm going to bound this LP norm by P minus 1 power Q over 2. And then the L2 norm. And I am happy with the L2 norm because, as I mentioned already, the L2 norm of such a quantity is very easy to compute because the Hermite polynomials are orthogonal. So here, when I have the L2 norm, so let me put it in red, this is something I can really easily compute. So I won't compute it because, okay, it's not the purpose, but just, okay, trust me, this is something which is easy to compute. And so when I compute it, this quantity here, so the square of this quantity, it is easy to compute explicitly and to prove that this is indeed less than nt minus s over n factorial q. So this is a factorial q coming from the isometry property of Hermite polynomials, and then the sum of rk power q. So this calculation, okay, takes maybe 5 minutes to write it down, but this is something which is quite easy to do. And now let me call R this guy, which is strictly bigger than 1 because P is strictly bigger than 2 in the Billingsley condition. So R is square root of P minus 1. And then if you look at what I just proved, it is exactly Ben-Harris condition because this guy here, so there is a square, so you will get with the square root. So this is exactly the square root we have here. And then everything in this constant, and in the constant you get exactly these quantities. So if this quantity is finite, you get the tightness, right? So the proof you see is very simple if you use this hypercontractivity argument. Okay, so now it's time to so that I give you my my statement with David. Okay, so this is myself and Nualart. So same context as in the BREUER-MAJOR theorem. So I have a phi which is square integrable with respect to the standard Gaussian measure, and which I assume to be of Hermite rank. Let's say D. The letter I used. Though I assume, which is what I need to get to have the FDD convergence, I assume that sum of Rk power D is finite. Okay, so let me let some place here, and then the conclusion is that tightness holds. So if this statement, so for the moment I have to complete the statement here, but just let me compare. So if I was stating Ben Harris or Chambers flood result, here I would put the condition that this guy is finite. Okay, so this would be my additional condition. Now, if you just follow what I did at the beginning, is that the BREUER-MAJOR theorem contains, as a particular case, the central limit theorem, classical central limit theorem. And maybe you remember that in the central limit theorem, the functional version, so the Donsker theorem, there is no additional property to pass from FDD convergence to tightness in D. So the usual central limit theorem tells you that if you start with a random variable which is square integrable, then without any further assumption, you have the Donsker theorem, so you have tightness. So there is nothing in the usual CLT, there is no additional property to add. If we compare with Chambers and Flood, we have this additional thing. Okay, so now let me write what we need to have in order to have tightness, what we need to add with David. We just need to add that my phi from the beginning, so this phi here is not only in L2, but actually belongs in LP for some p strictly bigger than 2. So it's very close to nothing somehow. We cannot. So it's like it's almost like an empty further assumption. We must have that phi is in LP with p for some p strictly bigger than 2, but which is something in general very easy to check. For instance, if for phi, imagine example, you take phi of x is absolute value of x, so which is not centered, so you just subtract square root of 2 over pi. This function has Hermite rank d equals 2, so it falls in the BREUER-MAJOR setting. So if R is square integrable, then you get tightness because phi is of course LP, it belongs in LP. Yeah, but for this phi, this condition is not satisfied. So, for instance, it was an open problem to know if BREUER-MAJOR, the functional version of BREUER-MAJOR, holds for the absolute value. So, with this criterion, we cannot get anything because this is not satisfied. But with our criterion, it's obvious. Okay, so now in the remaining time, I will just sketch the proof. Just to explain, so here I'm sorry, I will use Malema calculus. So I'm sorry not to use Malema calculus, but if some of you is not familiar with this, but okay, so yeah, it's really I really use Malema calculus in a deep way, and maybe I will just concentrate on the main difference with respect to my short proof of Ben Harris. So in order to do so, I use a shift process, which interestingly has been introduced by David and Arturo Jaramillo that you just recruited. They used this to prove tightness in a very nice paper about local times associated with fractional Brownian motion. And this is the same idea here. So the merit was to observe that indeed, if we use this idea in the BREUER-MAJOR setting, then we get something nice. So if we have a phi, which is some, as usual, sum of AQ, HQ, Q from D to infinity, then what we call the shift is just to consider something I will call phi D, which is the same sum, but where you replace HQ by HQ minus D. So here I put the minus D. Okay, so this is the shift of phi. Also, something, if I want to use Majorana calculus, I have to have somewhere a Gaussian process, and I can even use the standard brane motion. So I will, without loss of generality, I will assume that my sequence, my stationary Gaussian sequence GI is generated by Wiener integrals. So it takes the form of WE1, WE2, etc. So it has the same law. This is not an assumption, so I can always represent any stationary Gaussian sequence this way. So now this time the EIs are square integrable with respect to the Lebesgue measure, and my W is just the standard brane motion. Okay, and now I'm going to do the same starting point. So I look at the increment of y and t minus y and s LP of omega. And here, this p here turns out to be exactly the same p than we will that we have here. So it explains why we need p to be strictly bigger than 2. So this is here that this thing comes from. Okay, so here I do like I did also in my simple proof of Benaris. So I can rewrite this like ns plus 1 nt, and then you remember in my previous proof what I did was to expand phi in Hermite polynomials and to apply triangle inequality and then to deal with the hypercontractivity property. Here I am trying to keep an equality, so I am not going to apply the triangle inequality, because when I do so, somehow I lose the Hilbertian structure of the problem. And in general, we know that it sometimes does not give rise to nice bonds. So here I will just represent my phi of gk by using the shift operator, which has some regularizing property. So I write this, so I am sorry for those of you who are not very familiar with Majorana calculus. So yes, just LP of omega, but just let me describe the idea is to, so this is the iterate Skorohod integral of order D, and this is the shift operator. And this operation has a regularizing effect. And this is what we are going to use. And here is a key argument. We use Mayor inequalities to bound this quantity by a constant depending only on P, and then a sum over L between 0 and D, which will be the derivatives of my shift operator. And then I have still, so this 1 of square root of n. And then I can remove this delta D, which is not easy to, this is not easy to deal with this delta D. So Mayor inequalities somehow can transform bonds on delta D to bonds on the Majorana derivative, which is an easier mathematical object to deal with. So I get this. Okay, and still LP. Okay, so and now what I do is that, so I say that this is so this is a little trick here, not very a trick, but I say that the LP norm is the LP over 2 norm of the square. And when I so let me do here, let me write here, or maybe I need some more space. So here I have the LP over 2 and here power 1/2. So just I use that the LP norm is the square root of the LP over 2 norm. And so I can take the square of what is inside. And so by doing so, so maybe I obtain a double sum k prime. And then I have my shift at gk differentiated L times, because I apply the Majorana derivative and I have the chain rule. And then I have the L gk prime. And then the way this guy disappears is that it gives rise to rk minus k prime power t. And so power d plus r. Okay, and so I get this quantity. And now I am more or less done. Why? Because the only things that are still at random here, which are random quantities, are these two guys here. The rest is completely deterministic and completely related to the de-integrability of R. Okay, so maybe I just keep this. Oops. So here, up. I will put these guys in the next sheet. Okay, and now I just observe, so it was part of the proof of our result, that if we take the supremum over K, which is not really a supremum because the quantity is constant that I'm going to write is constant with respect to GK, this norm here, this LP norm, is exactly finite, is finite. So this does not really depend on K because GK are just a standard Gaussian. And so here it is actually the fact that we are dealing with the shift operator. We differentiated L times and we apply to standard Gaussian. And the fact that it is finite, so we have to prove it, but this is very much related to this assumption we do here, and also to some sort of semi-group proof, which are quite classical for people, also specialists in the semi-group theory. And so if I use this, now I just apply all the inequality, and I get that this is less than a constant. So this constant comes exactly from this finiteness here. And what remains is exactly 1 over n, the sum of Rk minus K prime d plus L with some absolute values over K and K prime power 1/2. And this is no longer random quantity. This guy, it is easy to see that this is less than nt minus ns over n power 1/2, since R is de-integrable and bounded by 1. Okay, so we can just make the usual transformation. You put A is K minus K prime and blah blah blah. And so you get, if we look at what we obtain, we get that the LP norm of the difference between Y and T and Y and S is less than a constant that we got finite by this property, which once again is related to this assumption here, times this nt minus ns over n 1/2, which was exactly what we need, which is exactly this condition here, which is satisfied. Okay, yeah, okay, so maybe I stop here. It's a good place to stop, I think. And so my talk and the proof. Okay, thank you very much. Maybe I put my video again.
So thank you very much, Ivan.
Yeah.
So are there any questions for Ivan?
Yeah. Hello, I have a question, a quick one.
Yeah, hello.
How about non-central limit theorems in the functional sense? For example, can you obtain like tightness results, for example?
Yeah, actually it's a natural question, but this is surprisingly, this is very easy in this case, and let me explain why. So it was already, for instance, given in the Takus paper I mentioned, or even De Breuer and Major. And the reason is that in the non-central limit theorem, the limit you get is, as I mentioned, the so-called Hermite process. And one of the properties of Hermite processes is that it has trajectories which are either continuous or further strictly bigger than 1/2, right? For Brownian motion, it is exactly 1/2 or 1/2 minus. And so for Hermite processes, it is h minus, where h is strictly bigger than 1/2. And now if you look at my tightness result here, because here we know that the limit is more regular than 1/2. You can still keep the 1/2 which is here, but you can, it allows you to take p equals 2 here. So you are not in the critical case where p must be strictly bigger than 2. Here you can choose p equal to or even less than 2. And in this case, it means that there is no difficulty in checking this tightness in this case. So because the process in the limit is more regular.
I see, thank you. And also for the semicircle case, for the non-commutative case, can you obtain something like this? For example, like convergence to free Brownian motion or something like this with semicircle distributions instead of Gaussians?
Yeah, so it's a natural question. So we have the exact analog of the BREUER-MAJOR theorem with FDD convergence in free probability. So you just replace standard Brownian motion by free Brownian motion, and you just replace GKs by semicircular distributions. So we managed to prove this, and actually it was using also the Mayer-Einstein approach and its extension to the free probability world that I did with my co-author, so Roland Speicher, but the functional version is not even clear what it means because you don't have tightness result as far as I know in free probability, and it's not really processes in the classical sense. So you even to give a meaning to what functional version would mean is not clear to me. So maybe you are more specialist than me, but I am not sure that the question in itself is well posed.
Yeah, maybe with the empirical distribution, something like this. I don't know. But
yeah, but maybe but for sure, if we do yes with the empirical distribution or something else, so it's quite far from what I did here, and so to be honest, I did not think about this problem at all, so I have no idea.
Okay, thank you very much. Really nice talk. Thank you very much.
Yeah, thank you.
Are there more questions or comments?
Yes, I have a question, please. In your hypercontractivity, is this closely related to hypercontractivity and the log-Sobolev inequality in the context of the paper of Gross, or is this something a bit different? Yes.
No, it's exactly this. So I mean, here I'm just using the vocabulary of Wiener causes and so on. But it's like you apply a polynomial transformation to a Gaussian vector, and you get that if the degree of the polynomial is fixed or is bounded, then you get the same, yes, hypercontractivity of Gauss and so on. So this is exactly this.
Okay,
so
thank
just using my language.
Oh, okay, thank you.
Yeah.
Nice talk, thank you.
Thank you.
So maybe if I can make a small comment regarding actually both questions. I guess you proved, or maybe it was Totkem, that certain actually stronger contractivity properties holds for the Wiener chaos, right?
Yeah, so this is Bian and Speicher result, I think.
Yes, sorry. So then actually a similar condition to the one in Billingsley, should be proved easily, but maybe what this implies is what is not clear, right?
Exactly. So the link with tightness or whatever it could mean in free probability is not clear. But as you say, so the proof which is displayed in the screen here should work exactly the same way in the free probability case. But then we have to interpret what it means, and this is not so clear. Because in Billingsley, so this is related to tightness because he's checking the compact sets in D01 in the scored space and then relating to this quantity and so on. But this has no sense at all in the free probability setting.
Okay, and maybe just a very small, maybe obvious answer is the p bigger than 1 is necessary. So there are examples where p equals 2 is not enough.
Yeah. In Chambers and Slot, there is a counterexample. But to be honest, I don't understand what is written. So they claim that they have a counterexample of situation where if you take p equals 2, so if you don't have if you consider, so there is a counterexample in the situation where you have no additional assumption, so you just would have this. So if sum of RK power d is finite, then they found, as far as I understand, they found a counterexample for which you don't have tightness. So it means that we are forced somehow to put something more. But I don't understand the counterexample, so for me, it's not so clear. But it's, yeah, I mean, what I mean is that this is not like in Donskoy's theorem, as far as I understand, in the sense that you cannot expect to have tightness in any situation just under the assumption that the sum of RK power d is finite. You need something more.
Yeah, thank you.
Yeah.
So if there are no more questions, let us thank Ivan for his very nice talk.
Thank you.